Today's lecture, we're going to talk about a little topology, and topology is basically about open sets and what they're good for. There are going to be a lot of definitions on this, and a lot of things to memorize for the exam, and so I suggest you pay attention. So we start out with the first set of definitions. We're going to define an open set itself. An open set is let U be a subset of the real numbers. We say that U is open if for every A element of U there is a delta greater than 0 such that A minus delta, A plus delta is contained in U. Okay, so first of all, our open intervals are going to be open sets, but there are much more complicated open sets than that. An open set is, in some sense, a set where every point in that set has a little elbow room around it. Okay. An open cover. Okay, what do I mean by that? Well, here I'm shifting. We're going to start out talking about let S be a subset of real numbers. So S is going to be something that lives on the number line. Okay, let script U, and okay, note I'm using a different font here. This is because U is going to be a set, but it's not going to be a set of real numbers. It's going to be a set of open subsets of the real numbers. So script U is a set of sets. That's why I give it a different font. We say that U covers S, or that U is an open cover of S, if for every point in S there is a set U sub S in this script U, so that which contains the point S. So it's complicated, but I'm using, the fact that this is a lowercase s means it's an element of this set S. The set S in the plain font is a subset of the real numbers. This U sub S here, which is in the plain font, it's also a subset of the real numbers. So I have this S in my script S that's in my US, and my US is one of these sets in my script S. Okay. To make this a little less confusing, you might want to start thinking of the points on the real line like marbles or peas or something, and the elements of my cover to be cups. Okay, and so this set of cups covers S if all of the little marbles in S are contained in one of those cups that are in my collection of cups U. If that helps you, fine. If you get it just by the plain language as it's written, go there. This is a concept we're going to be living with. Okay. Now, a partition. Okay, what's this? First off, this is a place where analysis uses a word that algebra uses, but we use it with a slightly different way. Okay. Similar in intent, but different in how it plays out. So let the closed interval from A to B be an interval in the set of real numbers, and of course the lower endpoint is lower than the bigger endpoint. A partition of AB is a finite subset of AB that contains the endpoints. Okay. Partition here, we're using it in the sense of walls. We want to partition up an office using walls. You might have seen a big room that they put up put partitions in to cut it up into pieces. This is what we're doing. We have two main walls on this closed interval. They're the points A and B. They're what chop it off from the rest of the line. But we're going to have a finite subset of this to cut it into smaller pieces. So we will use a notation that P is equal to A naught less than A1 ... less than Xn, X naught less than Xn is equal to B. And these points, these X sub i's, are chopping up my interval into subintervals. And so I'll have the interval from one point in my partition to the next point in the partition is going to be a subinterval of P. Okay. Now we have our partition. We can refine our partition, right? What does that mean? It's if P and Q are partitions of AB and P as a subset of Q, we say that Q refines P, or it's a refinement of P. The idea is Q is going to contain more points than P. It chops it up into finer pieces. It makes it better because we're going to be using these partitions so that if they're chopped up finer, they're a better approximation of something, and we'll get to that before too much longer. Okay, and there'll be a particular type of refinement that we'll use. So given a partition P of AB, we P prime is obtained from P by adding midpoints if P prime is P plus all of the little midpoints of each of these subintervals. Okay. All right. Well, that's a lot of definitions. We've had 3 pages of definitions. We need to use them to prove something. Okay. Let U be an open cover of AB, and let P1, P2, P3 be a sequence of partitions. Each partition refines the previous ones. And we're going to say that each partition is made from the previous ones by adding the midpoints. Okay, we're chopping these up. Each of the intervals is half as long as the previous ones. We're just taking our knife and chopping it up like you're chopping up carrots or something. Then there is a K such that every subinterval of PK has to be contained in some element of U. Okay, so regardless of how small the elements of U are, we will be able to find one of these PKs so that everybody is in one of these guys. Okay, it doesn't take buddies to cover them up, that one of the sets is enough to cover up the subintervals of any particular subinterval of PK. And we're going to prove this by contradiction. We're going to say, okay, regardless of how fine we chop them up, we're never going to, if we choose any K, there'll be some subinterval, okay, in my P sub K that is not contained in any of my open sets that are elements of my script U. Okay, so in fact, for every K, we've got this set of subintervals. We can assume that IK contains IK plus 1. So let's think about this. So what does this mean? It means if at IK plus 1, it means that there is none of my U's cover it. Okay, none of my elements of U covered it. Well, if it wasn't covered at the K stage, it's not going to be covered at the previous stage because this is smaller than this one. If this wasn't covered okay, then this one wasn't covered either. Okay. So we can assume we've got this set of intervals going all the way up, okay, and none of them are contained in anything. Okay, so given this, we have, let's say it, nested intervals. And so this means we can apply the nested interval principle. By the nested interval principle, there is a unique point C that is contained in all of these I sub k. Okay, so, all right, so we've got C. We've got one single point C. So we've got, what do we know about U now? Let's talk about script U now. It covers up the closed interval AB. Since it covers up AB, there has to be some element of it that contains that single point C that we work so hard to get. Okay, since this UC is open, there's a delta, so that C minus delta to C plus delta, that open interval, is contained in my U of C. Okay, so there has to be then some particular K so that the length of I sub k is less than the delta. So the C is in the I sub k. The I sub k is short, so it has to be contained in this C minus delta to C plus delta. But aha, okay, by our construction of k, some part of IK always has to flop out from under these U's. So we have a contradiction, and we're forced to conclude that we do in fact have a particular K where everything is chopped up small enough. Some corollaries for this, okay? Given an open cover U of AB, there's a finite subset of U that covers AB. Okay, so the idea is, the sets that are in U might be really, really small, and it might look like it takes all of them to do it. But what this is saying is that no, a finite number will do. Okay, if the whole collection covers up a finite number. Now, how do we do this? Well, our proof would be, start off with a partition. Okay, just the one that just contains the endpoints A and B. Okay, then add a midpoint to that, add midpoints to that, and keep on going down, adding midpoints. By the previous theorem, there is a K so that, hey, any subinterval of this is contained in some element of U. And so there are only a finite number of subelements. And so each of these must be contained in some element of U. So there's a finite number of sets. Take this finite number of sets. Since they cover up all of the subintervals, they'll have to cover up the whole interval itself. Okay. This next one is going to strike you as a little strange. Okay, suppose that U and V are open sets of the real numbers that, okay, they don't intersect each other, and their union contains AB. It says then, if A is an element of U, then V intersect AB is empty. Okay, so how do we prove that? Well, we do the same thing because U and V is basically an open cover. We'll have to be able to chop up this interval into pieces that is covered by U and V. Okay, well, start out with your closed subinterval, well, your point A. Okay, then A2 is contained in a subinterval of this partition. It'll be contained, all be contained in U, and you can just start piecing it together all on up. And so that all of A through B is contained in U. And so since U doesn't intersect V, then V can't intersect AB. And so these give us a couple of more definitions. The first one, a compact set, whenever S has the property that any open cover of S has a finite subset that also covers S, we say S is compact. Okay, this is going to be used all over the place. Okay, it's a very important property for a set of real numbers to have. And a set is connected. We say whenever S has a property that there are no disjoint open sets U and V such that S is contained in U union V and both S intersect U and S intersect V are non-empty, we say S is connected. So this is basically saying we can't separate S into two different pieces. Okay, getting them separated under different open sets, we can't do that. Okay, and stop sharing, and then I will stop recording.